Welcome to JCE eConnect. Hello friends, in this video I will explain how to solve the problems on one-dimensional bar element. The problem statement is: consider a bar as shown in the figure. Using elimination approach, determine the following. First one, nodal displacements. Second, stress in each element. Third is reactions. In this diagram is given like this. It is a stepped bar. At the both extreme ends, the bar is completely fixed, and there are two loads are acting. One is 10 kilonewton towards right side, and there is 20 kilonewton towards left side. In this problem, he has not mentioned which direction we have to assume positive. So it is our choice. I will assume towards right side is a assumed positive direction. So 10 kilonewton is acting towards right side, that I will take it as positive value. 20 kilonewton is acting towards left side, which is opposite to the assumed positive direction. That's why I will take it as negative, minus 20 kilonewton. Step number 1, FEA model. In this step, we have to draw line diagram of bar element and represent all the nodes, and we have to do the node numbering here. Node numbering is done like this. At extreme left side, I have taken node number 1, and the point where 10 kilonewton is acting, that I will consider as node 2, and point where 20 kilonewton is acting, that I have considered node number 3, and extreme right side I have taken as node number 4. We can do in reverse way also. Starting from right side, there I can take it as node number 1, and extreme left side I can take node number 4. This is also possible. Now according to this node numbering, what we have taken, I will explain now. At node 1, displacement is Q1. Similarly, Q2, Q3, Q4 are the displacements at node 2, 3, 4 respectively. And here I have written E1. E1 means element number 1. For E1, node numbers are 1 and 2. For E2, node numbers are 2 and 3. For E3, node numbers are 3 and 4. And F1 is the force acting at node 1. Since there is no force acting at node 1, F1 is 0. At node 2, here 10 kilonewton is acting, so F2 I will take it as 10 kilonewton. At node 3, a load of 20 kilonewton is acting. F3 I will take it as 20 kilonewton. Since it is acting towards left side, I will take it as minus 20 kilonewton. And at node number 4, no force is acting, so F4 is 0. Next step is elemental stiffness matrix. General equation is like this: K equal to A E upon L, 1 minus 1 minus 1. Here suffix 1 I have written because it is for stiffness matrix for element number 1. K1 equal to A1 E1 upon L1. You know that for element number 1, all the values are given here. Cross section area is 150 mm square. Length of element number 1 is 75 mm. E, Young's modulus, is 200 into 10 to the power of 3 megapascal. Substitute all the value here. A1 equal to 150, E equal to 2 into 10 to the power of 5, L1 equal to 75. Calculate this part, AE upon L, that we are getting as 4 into 10 to the power of 5. 10 to the power of 5 I have taken outside the matrix. only 4 I have multiplied inside. This is for calculation purpose to make it the procedure easy. And whatever the value I have taken outside, that is 10 to the power of 5, the same common value has to take for the further stiffness matrix also. Then it helps us while adding the all stiffness matrix to get global stiffness matrix. Similarly, find out the stiffness matrix for element number 2. Here K2 equal to A2 E2 upon L2. Substitute all the values. Similarly, you have to follow the same procedure what you followed to find stiffness matrix for element number 1. That we are getting as again 4 into 10 to the power of 5. Here also I have taken 10 to the power of 5 outside and 4 I have multiplied inside now. Now K2 becomes 10 to the power of 5, 4 minus 4 minus 4, 4. Similarly, find K3 also. One important thing we have to observe here, I will take K1 here and I will explain. See, for this matrix, columns and row numbers I have given as 1, 2. Why particularly the number 1 and 2 only? That is our question. That will be clarified. See here, looking at the diagram, FEA model diagram, for element number 1, the nodes are 1 and 2. That's why column and row numbers I have taken as 1, 2. For element number 2, that is in stiffness matrix 2, K2, I have taken as row and column numbers 2, 3. Because in the line diagram, we can see that for element number 2, nodes are 2 and 3. Similarly, for element number 3, nodes are 3 and 4. So, row and column numbers are 3 and 4. You can see in the K3 stiffness matrix for element number 3. Like this, we have to find stiffness matrix for all 3 elements. Next step is to find global stiffness matrix. Global means it is a stiffness matrix for entire element. This we can get by adding all 3 stiffness matrix. Equation I have written here, K equal to K1 plus K2 plus K3. Addition of all stiffness matrix is very important step here. So, to understand this one easily, what I will do, first I will write a matrix, blank matrix, and I will represent their row and column numbers. Since there are 4 nodes, the size of the global stiffness matrix will be 4 cross 4. First I will write all 4 column numbers and row numbers 1, 2, 3, 4, 1, 2, 3, 4 columns also like this. 10 to the power of 5 common, that's why I have written outside. Now I have to fill all the elements inside the matrix. For this we have to follow one procedure. See here in the place of column 1 and row 1, I have written there an arrow mark and a small box. That place belongs to column 1, row 1. What I have to write there? See here in the global stiffness matrix, in that place I have written 4 in the place of column 1 and row 1. How it comes? That we will come to know by looking at elemental stiffness matrix K1, K2, K3. See here in K1, in the place of column 1 and row 1, here also I have given row and column numbers. Look at that, column 1 and row 1, the value is 4. That's why in the place of column 1 and row 1, I have written 4. Next, in the row, second element, column 2, row 1, I have written there minus 4. You can check there. In stiffness matrix 1, column 2, row 1, in that place minus 4 is there. That's why I have written here minus 4. Similarly, you have to go on writing all the values. Next is column 3, row 1. Check there. This one, column 3, row 1 is not available in all 3 matrices. So, that value I will write it as 0. Next, column 4, row 1. Here also I have written 0. Check there. Here in K1, K2, K3, we won't get column 4, row 1 value. So, I have written as 0. Similarly, go on adding all. in some place, we will get two values. For example, column 2, row 2, I have written there 8. Come back here. See, in K1, column 2, row 2, at that place we have the value as 4. Similarly, in K2, again one more time, column 2, row 2 is there. There also we have the value as 4. So two values will come in the same place. So I have added those two. 4 plus 4, that becomes 8. So here, in the place of column 2 and row 2, I have written 8. Two values are coming there, 4 and one more value is again 4. Add these two, we will get it as 8. Similarly, in the place of column 3 and row 3, I have written there 12. Because again, same here also, two values will come. Look at the stiffness matrix 2. At column 3 and row 3, value is 4. Look at K3. In stiffness matrix 3, at column 3 and row 3, the value is 8. So two values are coming there. One is 8, one is 4. So add these two, we will get it as 12. See, in the global stiffness matrix, in the place of column 3 and row 3, I have written as 12. This is one of the very, very important step. Next step, global displacement vector. Write down all the displacements. Q equal to Q1, Q2, Q3, Q4. Next step is step number 4. Force vector or load vector. F1, F2, F3, F4. F1 is 0. In the starting I have explained why we have to take F1 as 0. And F2, 10 kilonewton. F3, minus 10 kilonewton, 20 kilonewton. F4 is 0. Next step is equilibrium equation. K, Q equal to F. K is global stiffness matrix. We found already. Q, displacement vector, that we can find in step number 3. F, force vector, that we can get in step number 4. Write down all three which are already available. Next step is applying boundary conditions. Here we are solving this problem by elimination approach. So we have to eliminate particular row and particular column. What is that number of that column, number of that row to be deleted? That we will come to know looking at the diagram. One thing we should know that wherever the displacement is known for us, it means at what particular node displacement is known, that particular row and column number has to be eliminated. Look at the diagram. See here, at node 1 means extreme left side, it is completely fixed. So displacement will be 0. It means Q1 equal to 0. And extreme right side at node number 4, here also it is fixed. Displacement will be 0. It means Q4 equal to 0. So at node number 1 and at node number 4, displacement are known for us. That is, both the values are 0 and 0. So that particular row and column numbers has to be eliminated. It means row 1 column number 1 has to be eliminated. Similarly, row 4 column number 4 has to be eliminated. That I have done here. You can see here. See, in this equation, row 1 column 1, row 4 column 1, 4 I have eliminated. I have struck out. Remaining values that I have written here: 10 to the power of 5, 8, minus 4, 12, Q1, Q2, Q3, 10 kilonewton of force, minus 20 kilonewton of force. This matrix I will write in the form of matrix, in the form of equations, and solve them. We will get Q2 and Q3. Q2 we are getting as 0.005 millimeters. Q3 minus 0.015 millimeters. Next, this is how to find the displacements. Next step is how to find stress in each element. To find the stress, the equation is sigma equal to. Here I am finding for element number 1, so I will mention it as sigma 1 E1 upon L1 minus 1 1 Q1 Q2. This is a general equation for element number 1. Here I have written as Q1, Q2 because for element number 1 the nodes are 1 and 2. That's why I have taken as Q1, Q2. Substitute the value of E, L, Q1, Q2 which are known for us. Calculate this part. Sigma 1 we are getting it as 13.34 megapascal. Similarly for element number 2, sigma 2 E upon L2 minus 1, 1, Q2, Q3. Q2, Q3 because the nodes for element number 2 are 2 and 3. That's why Q2, Q3. Similarly, calculate this one. Sigma 2 we are getting as minus 53.34 megapascal. And for element number 3, in the equation I have written as Q3, Q4 because for element number 3, nodes are 3 and 4. Substitute here and find the value of sigma 3. That we are getting it as 50 megapascal. This is how to find stress in each element. Last part of the problem, that is finding the reactions. For that, the equation is like this. K equal to KQ minus F. R means reactions. K global stiffness matrix, that we know that. Q displacement vector minus F means load vector. Substitute all the values and calculate this one. Initially, what I will do, I will multiply two matrices, that is matrix K and matrix Q. Whatever the answer we are getting, that we will subtract with the force vector. After subtracting, we are getting the values as R1 equal to minus 2000 Newton, R2 0, R3 0, R4 12,000 Newton. R2 and R3, if you get a small value compared to these two R1 and R4, they are negligible, we can write it as 0. This is how to find the reactions at the support. At the end, I have listed all the answers. This is the method to solve the problems on one-dimensional bar elements. Thank you.